Hello class, welcome to our presentation on solar energy systems for Mechanical Design 2, our first project. And our team is composed of myself, Vila, Alonso all the way at the end, and Aranega.
So here we have our presentation overview. We're going to be going over the historical backgrounds of these solar energy systems, a brief introduction to them, and then solar energies, solar cells, the heat collectors that we can use with the solar systems, and then we're going to implement or talk about the environmental impact and the system overview at the very end. Here we have the historical background of these solar cell systems, which were first discovered in 1876 by Professor William Adams. He discovered this by illuminating a junction between a platinum and selenium plate, which produced a photovoltaic effect. At the time, this was considered a significantly of the most far-reaching importance. Domestically, though, these systems started to become available in 1950s, even though they were not very cost-effective, upwards of $300 for a single watt solar cell. They were, however, used in small toys and radios at the time, as that was the most common application. Through time and further research, the cost of these systems has started to reduce, as well as the overall efficiency gotten a lot better. Here we have an introduction to the current situation we have with solar cells. On a daily basis, the Earth is receiving 120 terawatts of radiation from the sun. This is 20,000 times the energy required to power the Earth. Not only does this meet the current demand without compromising anything towards the future, but it also reduces our dependency on fossil fuels, all while having zero emissions in a fully implemented system.
In this slide, we can actually see a side-by-side implementation of a photovoltaic cell and a solar thermal collector. Now, light is being converted to electricity by the solar panels. That electricity is then conditioned for home use by an inverter, and the generated electricity is used in the house, or when not needed, it can be actually sold back to the national grid. In the thermal side, we can see here an array of copper tubes with water flowing through it, which is implemented inside of the solar panel. The light is absorbed by the black surface in the solar panel, causing it to heat up. Now the water absorbs this heat, and it can actually be stored in a storage tank for daily use. Solar can actually save around 60 to 70% of energy during heating throughout the year. Here we can observe some of the pros and cons of solar energy. Some of the pros being that it is renewable, abundant, and sustainable. It is environmentally friendly, and we can obtain financial support from state and local government. Now, some of the cons are that it is expensive, intermittent, because we have day and night periods. Energy storage is expensive. It is made out of exotic materials, and it does require a lot of space. These are some of the solar cells that we will be covering during the next slides. In this slide, we can observe monocrystalline solar cells and polycrystalline solar cells. Now, monocrystalline cells have an efficiency of about 15 to 20%. They have a high silicon purity, high space efficiency, long-lasting, and low maintenance. One of the downsides is that they have a high cost and high manufacturing cost for that matter. The manufacturing involves grabbing these large high-purity silicon ingots and cutting them. And that cutting process is the one that raises the manufacturing cost because there is a lot of waste. Now, on the other hand, polycrystalline cells have an efficiency of 13 to 16%, slightly lower, but they also have a long-lasting capability. They have a low manufacturing cost, overall a low purchasing cost, and low maintenance as well. Though they do have a low space efficiency compared to monocrystalline cells, but they also have a low silicon purity. Next up, we have string-ribbon solar cells, which have an efficiency of about 13 to 14%. Now, they get the name because of the manufacturing process, which is used by the process of thin silicon ribbon pulling. Now, it is manufactured by pulling thin strands of silicon through molten high-purity silicon. They also have a long-lasting capability, and their main downside is that they are very low in space efficiency, they have a very high research cost, and a high manufacturing cost because of their process. Now, on the other hand, we have thin-film solar cells, which are commonly found in domestic use. They have an efficiency of 7 to 13%, On average, we can see 9% efficiency in these solar cells. They're made out of thin layers of photovoltaic material. They have a very low manufacturing cost because they can be mass produced. Now they have a low maintenance, also a low space efficiency, and a very fast degradation.
Another type of solar energy system is a solar thermal collector. It works on the principle of absorbing solar radiation in the spectrum of ultraviolet to infrared. It's commonly used to heat up fluid and for various applications. Specifically, it can be used for space heating for buildings, water heating, and steam production. Down here you can see the four main types of collectors that we will be discussing in the following slides. As you can observe here, we have the unglazed solar collector. It's most efficient in heating up large volumes of water or air, and it's most commonly used in domestic applications such as pool heating. It's also the least expensive of all the collectors due to its low manufacturing costs and implementation costs. Similarly, we have the flat plate solar collector. It has a very simple construction as well. It's most effective in space heating and water heating. And it has a reduced efficiency in cold climates due to heat losses associated with it. Another type of solar collector is the evacuated tube solar collector. It has a better heat retention than the flat plate collectors, but it's harder to assemble due to its complexity and requires more maintenance and upkeep. This solar collector also has a really low performance in cold weather. Lastly, we have the concentrating solar collector, which is comprised of a curved mirror and a receiver tube that runs along the center of that curved mirror. The sunlight is then reflected off of the mirror towards the center to the receiver tube, which then heats up cold water into hot water. This hot water can reach very high temperatures and can even become steam. This steam can be then used to power a steam turbine and generate electricity at a later state. This system is most efficient when used in large-scale applications. It's very large and a complex system due to the fact that it may require a 1 to 2 axis system to be able to do sun tracking.
Some key environmental impacts that these solar systems have is that they provide a significant environmental benefit in comparison to the conventional systems that we're using today, be it fossil fuel or anything else. They contribute to the sustainability of developments in human activity, all while reducing the CO2 emissions that are produced while operating these systems. The key and most important thing to take into consideration is the accelerated rate that we are providing electricity to these developing countries that are in desperate need of it. This, all in all, improves also the water quality, as there is no toxic waste produced in the solar systems. And it also allows us to reclaim the degraded land in order to implement these systems and build them. Here we have some of the overview of our presentations and the key points about it. The main advantage of these solar energy systems is their zero emissions. They allow us to not exhaust any of the natural resources that are limitedly available and can be used towards other applications, all while providing a significant socioeconomic benefit to the environment and restructuring the energy market. Potential environmental impacts can be minimized if taken the appropriate manufacturing and installation processes or measures. Ultimately, it is up to the involved factors to make the appropriate decisions by taking environmental issues into serious consideration.